All right, hello everyone, and welcome back to these astronomy talks. So last week we talked about the Milky Way and what we know about the Milky Way, and just like what we did with the sun, where we took what we knew about the sun and kind of extrapolated to the rest of the stars, we're going to take what we learned about the Milky Way and extrapolate it to the rest of the galaxies in the universe. This talk today is going to be a mix of two different things. You can kind of see in the title that we're going to be talking about galaxies and the foundation of modern cosmology. And so we'll get kind of a very general overview of galaxies. We'll go into a bit more detail about how they evolve and what's happening in them next week. So at the expense of starting to introduce some ideas about cosmology. How do we measure distances in the universe? How do we tell the age and the size of the universe using galaxies as that kind of distance indicator? So a bunch of different things today. We got a lot of stuff to talk about. So let's go ahead and get started with tonight's quote. And that is from Neil deGrasse Tyson. With every step, every window that modern astrophysics has opened to our mind, the person who wants to feel like they're the center of everything ends up shrinking. And this is where we're going to start talking about really big universe ideas. So if you start feeling that way, everyone's been through it if you study astronomy. So we're going to start with a very famous image. This is the Hubble Extreme Deep Field. This is an image taken by the Hubble Space Telescope covering just a tiny portion of the sky. If you held out your thumb at arm's length, this portion of the sky would be just a tiny little fraction of your thumbnail held at arm's length. To collect all this light, it actually took the Hubble Space Telescope 10 years to collect all the light because it's being used for other science over time. And so there's a total of 23 days worth of collected light in this image. Everything you see in that image, except for these three stars that I've circled here, everything in that image is a galaxy, from the big blobs that you see immediately to all little pinpoints of light that you see in the background. In fact, in this image, there are about 5,500 galaxies, the oldest of which were formed when the universe was still very young. The universe was only 200 million years old when the oldest galaxies in this image were formed. So extrapolating this number of 5,500 galaxies in this tiny fraction of the sky, we can extrapolate and tell us that there's more than 100 billion galaxies in the universe. Another thing that you might notice as you look at the Hubble Extreme Deep Field is that there's tons of different varieties of galaxies. So I've picked out a few here. There's some that look kind of fuzzy and kind of elongated. There's some that look like a beautiful spiral, just like the Milky Way. There's some that look kind of just spherical and ovoid. Furthermore, just in these three little snapshots, you can see different colors. That kind of ovoid galaxy is a very red color. In that same magnifying image, you can see some blue galaxies, some more yellowish galaxies. You can see different sizes. Some of them are as big as that red ovoid galaxy. Some of them are much smaller. The question we want to ask and what galactic astronomers want to answer is why is there just this wide variety of galaxy types, shapes, sizes, colors in the universe? Why isn't there just one type of galaxy? And that actually kind of poses an interesting problem in and of itself, because we are only able to see galaxies in these snapshots in time. We can't watch a galaxy evolve. We'll talk about galaxy evolution next week, but we can't sit there and watch it. That takes on the order of millions and billions of years, just like we can't watch a star evolve on human timescales. So instead, what we have to do is we have to look at many galaxies, Hopefully, they are all at different points in their galactic lifetimes, and we can sort of try and put together a picture of what galaxies look like throughout their lives. Now, to do that, that also poses a problem. There are a lot of problems in galactic astronomy because the local neighborhood, the Milky Way, the Andromeda, the Triangulum Galaxy, which is the background galaxy on these slides, and the smattering of dwarf galaxies in our local group, we're all pretty much the same age. We were all formed at relatively the same time. So instead, we have to look further back into the universe's past to see galaxies at earlier stages of evolution. And we can do that by looking at greater and greater distances, because remember, looking further away in the universe is looking back in time. So we've got to look at not only galaxies in different areas of the sky, but in different distances from us to get the full picture of why galaxies are like they are. So one of the big things that we know when we look at galaxies in the universe is that there are three very broad types of galaxies. So the first one we're very familiar with, the very beautiful picturesque spiral galaxies. These are going to look like flat white disks with some yellowish color in the middle signifying their bulge. And their disks, that's where all the cool gas and the dust is, and is interspersed with that hotter ionized gas going to glow that nice red color. And it's got beautiful spiral arms, giving it the name of a spiral galaxy. We've also got elliptical galaxies. These are redder, they're more rounded, they're usually elongated. And compared with spirals, ellipticals don't have any of that cool gas and dust, but they do very often have some hot ionized gas. And then everything else just kind of falls in the catch-all term of irregular galaxies. If it's not a disk-like, if it's not a spiral and it's not rounded, then it's irregular. We just kind of throw all the things that don't fit into the spiral and elliptical category into the irregular category. So let's talk about these types in more detail. So spiral galaxies, big beautiful ones. These are galaxies like the Milky Way. The Milky Way is a spiral galaxy, as we discussed last week. And just like the Milky Way, all spirals tend to have a very thin disk and a central bulge surrounded by a nearly spherical, nearly invisible halo. However, when we talk about spirals in general, the bulge size of a spiral can vary dramatically. It can be very, very tiny, or it can encompass almost the entire disk. So we'll simplify our discussion here and what most astronomers do into just talking about two galactic components in a spiral galaxy. We've got the disk, that hasn't changed. That's still the stars that follow those orderly circular orbits all in the same direction. All the dusty gas clouds where stars are going to be forming, all the supernovae happening, that'll all still be in the disk. But then we'll just combine the bulge in with the halo, because as the bulge gets bigger and bigger in a galaxy, it just kind of smoothly transforms into the halo. So we'll just call it all the halo component. So this is going to be the stuff that has very not much cool gas, it's not doing any star formation, doesn't have much dust. And the stars that it does have are going to be doing those random incoherent orbits, just like the Oort cloud in our solar system. So here's some examples of spiral galaxies. This is, of course, Messier 101, the Pinwheel Galaxy. This is Galaxy I study. This is an amateur astronomy image. We can clearly tell it's a spiral galaxy here by these beautiful, outstretched, extended spiral arms, very small bulge in the center. So it doesn't have even a moderately sized bulge like the Milky Way. It's a very small bulge in the center. Here's another spiral, sort of at a more tilted angle towards us. Still a small bulge. Here, it's not as easy to distinguish where the spiral arms are. This is more of a flocculent spiral galaxy, where instead of clearly distinguishable spiral arms, it's kind of got patches that make your eyes think it's a spiral shape. It's still a spiral galaxy. We'll still call it a spiral galaxy, but its arms aren't as well defined as other spirals. And here's an edge-on spiral, the Silver Sliver Galaxy. I dare you to say that a few times fast. Where you see it's edge-on, you can actually see the dust in the disk. You can even see a bulge where it gets a bit fatter towards the center. Maybe even the stars fading off into the halo as you move up and down from the disk. So still a spiral galaxy, even though it's edge on and we can't actually see the spiral arms, we know it's a spiral galaxy because of all that dust and gas there. Here's a very famous example of a galaxy with a huge bulge that just kind of blurs into becoming the halo. It's Sombrero Galaxy, Messier 104, where it's almost completely edge on to us. You can see the very thick dust lanes on the outsides of the galaxy. And then you see sort of the bulge, which is just generically there. And you see it kind of fade out into that very sparse halo. This is why I just call it the disk and the halo component, because the bulge size can grow to be very, very large, even for spirals. All right, so but not only that can bulge sizes vary, but the shape of the bulge can also vary to even form the appearance of a bar. So instead of a spherical bulge at the center, instead we have a line, a bar, a straight bar of stars cutting across the center. Like we talked about last week, the Milky Way, we think is a barred spiral galaxy. So instead of a spherical bulge in the center of our galaxy, we have a bar. A very good example of this is very famous, very picturesque NGC 1300, where you can clearly see it's got a straight bar. Then at the ends of the bars is where the spiral arms form and start to wrap around the galaxy. This is a very good, albeit a little dramatic example of a barred spiral galaxy. And then there are some galaxies that do have a disk and a halo component, but for whatever reason, they just lack spiral arms. They don't have those nice, clearly defined spiral arms. Instead, it is just kind of a smooth distribution. It's clearly flat in a disk. It's not, bulging around like an elliptical galaxy. It's clearly flat in a disk, and it will have a more concentrated area at the center that we'll call the bulge. But they don't have any of those beautiful spiral arms. These are called lenticular galaxies. They're sort of a halfway point between ellipticals and spirals. So here's a good example of one, NGC 4866, where you can sort of see the bulge in the center, and then the rest is, the disk. By the way, if you're wondering what NGC stands for, it stands for New General Catalog. It's just a big catalog of some bright objects in space. All right, so those are disk galaxies, spiral galaxies. We'll lump lenticulars in there with them. The second type is elliptical galaxies. So here, elliptical galaxies, they do not have a disk component. There is no spiral arms. There is no star formation happening in a disk in an elliptical because they just lack that disk component entirely. Instead, all they have is a halo component. So they might have a more concentrated region that you can sort of call the bulge, but really it's just kind of a smooth gradient. They're also not doing tons of star formation. They don't have a lot of that cool gas and dust for stars to form. So this means that they are going to look red and yellow because all they've got are the old red stars that are able to stick around for billions of years. Those hot, bright blue stars live for a few millions of years and then they're gone. So ellipticals just have those old red stars. So that's why they tend to look red and yellow. So here's Messier 59 in Virgo. You can see, there's a little region here where we might call that the bulge, but it's really just more of a smooth gradient until eventually you don't see any stars and you might be out of the galaxy. Another good one is Messier 105. Where there's a more tightly packed, but once again, just kind of a smooth gradient outwards. There's no disk, there's nothing, you don't even see any dust in here at all. In fact, you can sort of see the stars behind the galaxy and other galaxies behind this galaxy. So once again, ellipticals aren't doing much of anything, they're just kind of hanging out there. Ellipticals are some of the largest galaxies in the universe, can be some of the largest. But at the small end, we still got some ellipticals. We've got round and diskless, so they are elliptical, but they're much fainter than the bigger ellipticals. So we call these dwarf spheroidal galaxies. These are, because they're so faint, they are hard to see. We can really only see them nearby, out to maybe 20 million light years. Really, within our local group is where we can see them the best. But extrapolating out to the larger universe, we do think they populate the rest of the universe. It's not just something particular about our local neighborhood here. So for examples in our local group of dwarf spheroidal galaxies are like the Fornax dwarf spheroidal galaxy. So there's clearly no disk, there's no spiral arms, there's not really even much star formation visibly happening here, but you do see a cluster of stars, some nice blue stars, so maybe it's a bit younger, but not much is happening here. It's just kind of a bulge of faint stars here. Another good one is the Leo 1 dwarf galaxy. See here at the bottom of the image. This big bright star is the brightest star in Leo, Regulus. So every time you look up at the constellation of Leo and you can make out which star is Regulus, you are also looking towards another dwarf galaxy at the same time. So you can see, once again, no spiral arms, kind of bulgy, but very faint. So they are dwarf spheroidal galaxies. And then finally, irregular galaxies, like I said before, it's just essentially a catch-all term for anything that isn't quite spiral, but also isn't quite elliptical, sort of a miscellaneous class. So these galaxies can be white and dusty, like the disks of spirals or the young blue stars, just in whatever shape they want to be, caused maybe by an external force, maybe they just formed that way. It's different for every galaxy. So some good examples of irregular galaxies, a very nearby example is the Large Magellanic Cloud. You can see it sort of has a bar at the center, but it's also very irregular. Maybe it just has one spiral arm. The large and small Magellanic Clouds are special cases because they are currently interacting with not only the Milky Way, but also with each other. So that has probably changed their shapes in the past millions and billions of years. A very beautiful one is IC 4710, where you see tons of nice bright star-forming regions. There is perhaps a star-forming region, all these nice blue ionized gas regions, tons of nice bright blue stars. It's a very beautiful irregular galaxy, but once again, you can see it has no coherent shape. It's just kind of a collection of patches, sort of. Now, excuse me. Now, one of the early attempts to understand the relationships among galaxy types really focused on their shapes. And one of the first people to really focus on that was Edwin Hubble, American astronomer Edwin Hubble, whom the Hubble Space Telescope is named after. And he devised a classification system for galaxies that organized spirals and ellipticals onto the shape of a tuning fork. I don't know if you're familiar with that, but a two-pronged fork is what you need to know. Where we got ellipticals here on the left, lenticulars at the branch at the branching point of the two prongs of our tuning fork, and then spirals at the top and barred spirals at the bottom. So ellipticals, you can see here, are designated by the capital letter E and then a number 0 through 7, where the larger the number, the flatter the elliptical galaxy. It doesn't go all the way up to 9, just up to 7. You see these images of these ellipticals are going from very round at E0 to very elongated and flattened at E7s. The two forks, like I said, are the spirals. Capital letter S for ordinary spirals, capital letters SB for barred spirals. And then they're usually followed by a lowercase letter, where the lowercase letters denote their bulge sizes and the amount of dusty gas they have in them. So the bulge sizes decrease from lowercase a to d, and while the amount of dusty gases increase. So, for example, an SA galaxy will have a bigger bulge, not that much dusty gas. An SC galaxy will have a smaller bulge, a lot of dusty gas. And same thing for the barred spiral. So an SBA will have a big bar, not that much dusty gas. An SBC will have a smaller bar, a lot of dusty gas, extended spiral arms. Lenticulars, we will call an S0 or an SB0. We can distinguish a bar instead of a bulge. And then usually just tacked on, floating out beyond the two prongs of the sport, not shown in this image, are just irregulars. Irregulars don't even get a place here. So, and they're designated IRR, capital I, lowercase r for irregular. So this is the classification scheme that astronomers still use to this day. I want to stress, though, that this is not at all an evolutionary diagram. Ellipticals don't slowly grow spiral arms, become a spiral or a barred spiral, and it doesn't go backwards either. Even Edwin Hubble, when he wrote down this, his ideas about this back in the 20s, the 1920s, a century ago, he was very careful to say this is not an evolutionary diagram, and anyone who says it's an evolutionary diagram is asking for trouble. So this is just a pretty picture to classify galaxies. This has nothing to do with their evolution. We'll talk about that next week. Before we move on, I want to see, let's try your hand at classifying some galaxies. I'm not going to ask you to do elliptical because you actually got to do a bit of math to get the number. But let's look at two spirals. We've got the pinwheel galaxy on the left, Messier 101, and the barred spiral on the right, NGC 1300. So take a moment and think about what classification would you give both of these galaxies? I'll give you a hint. The pinwheel galaxy will be an S. You just got to figure out the lowercase. NGC 1300 will be an SB. You just got to figure out the lowercase. So take a moment and think about what classification you would give both these galaxies. All right, hopefully you figured it out now. Should have paused the video and think about it. I want to tell you, there are no, as long as you're not saying these are both ellipticals, there are no super wrong answers. In fact, astronomers will disagree with each other on what that lowercase letter should be. And in fact, we all tend to just use one person's classification that they did back in the 80s or 90s for this. So you can actually go look up what classifications these are. So that's what I've done. These are screenshots from the NASA Extragalactic database. On the left, you see all the various classifications for the pinwheel galaxy from Messier 101, different years. So if you said the lowercase letter should be C, then you would agree with these people from 1973. There are more complex classifications. You could also have said it's an SAB, has some faint ring structure. That's what the parentheses RS has. CD, you could combine the lowercase letters if you want. I didn't tell you you could, but you could have. You also not even look at that. You could say it's a type 1 extended UV disk. It could be a lopsided galaxy, a spiral with one heavy arm. It could be anything. Similarly, for HEC 1300, if you said that lowercase letter should also be a C, then you would agree with these people from 1982. You said it was a B, then you would agree with these people from 1981. See, it can even differ year to year. Here, someone's creatively called it, well, it's an NGC 1300 type. So at some point, you just come up with a classification and you work with it. So there are no wrong answers. If you're interested in classifying galaxies just in your spare time, there's a wonderful citizen science project called Galaxy Zoo, where you will help astronomers classify galaxies, because astronomers got other things to do besides sit here and just look at pretty pictures all day. I wish that's what we did, but we got other things we got to do. So if you would like to help us out and classify galaxies for us, Galaxy Zoo is something you should go look up. So those are the patterns in galaxy shapes. We've also noticed, thanks to modern astronomical surveys, that there are patterns in galaxy color and luminosity, just like an HR diagram for stars. There are HR diagrams for galaxies. So thanks to these modern astronomical surveys, we can get information on a large number of galaxies, their colors, their luminosities, tons and tons of information. And so rather than being very subjective and disagreeing with our collaborators on what morphological type a galaxy is, we can actually do more quantitative analysis of galaxies. And so we've seen, here you can see 4 different plots. A color is on the vertical, where really red is up top, really blue is down at the bottom, and then masses instead of luminosities. We can think of them as roughly equivalent, where low mass, low luminosity is towards the left, high mass, high luminosity is towards the right. And if we look at this, the top left plot labeled all galaxies, you see there are 2 big clumps here. We've got galaxies in the blue cloud and the red sequence. So those galaxies in the blue cloud have the hot young stars doing active star formation. That's what's giving them their blue color. Meanwhile, the galaxies in the red sequence contain older stars, red stars. Then they're not doing star formation. When we break up this plot into the morphological types, which you can see up here at the top right, we've limited to just elliptical galaxies, and the bottom right, just spirals. We see that the red sequence is populated by mostly elliptical galaxies. The blue cloud is populated by mostly spiral galaxies, which makes sense given what we already know about their star-forming properties. So this is a very cool thing to know, be able to do quantitative measurements rather than just subjective qualitative measurements on galaxy types. So there are patterns in their galaxy color and luminosity. By the way, the space in between the blue cloud and the red sequence is often called the green valley. And it's a lot of investigations going on into what types of galaxies are in the green valley. We also can look at patterns of where galaxies are in the universe. So most galaxies are gravitationally bound together in loose groups. So the Milky Way is in a loose group called the local group. So it's the Milky Way, Andromeda, Triangulum galaxy, and then a smattering of dwarfs, of irregulars. There are also some beautiful combinations, some highly compact groups, such as Robert's Quartet here, where you can see 4 spiral galaxies. Some of them have more distinct spiral arms, like this guy down the bottom's got these 2 nice spiral arms. This guy at the top left has 1 big wonky spiral arm. This one at the right is more flocculent. This one here, you can sort of see some faint shells, maybe some evidence of some spiral arms. These are all spiral galaxies doing some star formation in this compact group. They're all interacting with each other. That's probably why that one on the left has a big wonky spiral arm. So a lot of them are found in small groups. But there are also huge collections of galaxies that are called galaxy clusters. And these, instead of, tens, 50 galaxies in a group, here we've got hundreds or thousands of individual galaxies in a very concentrated region, usually only about 10 million light years across. So this image here is of the Virgo cluster. This is the closest galaxy cluster to us. And you can see, this is actually taken by my advisor here at Case Western. You can see all different types of galaxies, but what you mostly see are ellipticals. Here's an elliptical that kind of make up the 2 eyes of the space over here. Here's an elliptical down at the bottom left. There's an elliptical up at the top right. Elliptical galaxies make up half of the large galaxies in the clusters. There are some spirals. Maybe this is a spiral. There's a spiral down there, but they don't make up the cluster. Elliptical galaxies dominate clusters. And that actually leads to a very profound statement that the denser the galactic environment, the more dominant elliptical galaxies become in the population. This is a plot from a paper I know so well, I don't even have to look it up. I know exactly, but this is Dressler in 1980, where on the vertical is the fraction of population, so 10%, 90% at the top, where he was looking at clusters. On the horizontal is the local density, where it's not as a dense environment towards the left, a more dense environment towards the right. As we go to more dense environments, you see the numbers, the percentages of spirals and irregulars that make up the population decrease, while the number of ellipticals and lenticulars increase. So this is a profound statement. This means that spirals and irregulars are more likely to be found in those loose groups or in the field. That's what we just call a galaxy out by its lonesome. Whereas ellipticals and lenticulars are more likely to be found in those very compact groups or in those clusters. And the fact that elliptical galaxies are found at the center, near or at the centers of clusters, suggests that as spirals come in and collide with each other and merge together, they can actually transform themselves into ellipticals and lenticulars. Also, the most luminous galaxies are at the centers of the cluster, suggesting that they too have grown large by cannibalizing those galaxies that have gotten close, adding up, absorbing those galaxy stars into themselves, becoming brighter, more luminous, and more massive. So this is a very profound statement. Here we can watch a little animation of galaxies merging together in a cluster, forming essentially a big elliptical at the center, surrounded by maybe most of the ellipticals, maybe a few spirals on the outskirts. This is another animation done by my advisor here at Case Western. All right, so we've got a good census of what's going on with galaxies at this point. Let's now talk a little bit about cosmology and how do we measure distances to these galaxies, because distance is one of those key things that's going to help us unravel the true properties of the galaxies. Just like getting a true luminosity of a star, we've got to know its distance and then its apparent brightness on the sky. To get true information about galaxies, we've got to know their distances from us. And measuring a distance is one of the most difficult things to do in astronomy. Mass and distance are pretty dang hard because everything just sort of looks flat on the night sky. So to get distances, we sort of rely on this distance ladder, where each rung on the ladder builds off of distance measurements and calibrations from the previous rungs. So here you can see the distance ladder that we're going to be talking about. At the bottom is the easiest stuff to do, radar imaging. So by shooting radio waves at the planets in the solar system, they will reflect off of the planet's surface or maybe the cloud tops and then return to Earth. And because radio waves travel at the speed of light, the time it takes for that radio wave to hit the planet and return back to Earth is only a function of distance. And so that will tell us a distance. So that's how we measure distances on the scale of our solar system. That's how we know that one astronomical unit, the distance between the Earth and the Sun, is about 150 million kilometers. Because we shot a radio wave at Venus, it bounced off of Venus. So we know the Earth-Venus distance, and then doing some geometry, we can figure out the Earth-Sun distance. That's the simplest bottom rung of our distance ladder. The next step up is a technique we've already talked about extensively. So remember, that's parallax, where the apparent shift in the position of a star as the Earth orbits the Sun. We can measure that angular shift, and that angle only depends on distance. And so that will actually give us distances for stars in the Milky Way up to about a few thousand light years, especially with the addition of the Gaia spacecraft back in 2013. We're getting really good distances for nearby stars in the Milky Way. Can't use it for anything outside of the Milky Way. So that means we've got to rely on other distance measurements. So before we talk about Cepheid variables, whatever those are, let's talk about standard candles for a moment, because this is a very important concept for pretty much all the rest of the rungs of the ladder. So standard candles are objects for which we already know their luminosity. And then we can go measure their apparent brightness on the sky and invert that, do some math to get a distance. So for example, say we got a 100-watt light bulb. And we know it's 100 watt because the people in the factory who make the light bulbs wrote on the light bulb 100 watts. Now, if you go hold that lit up 100-watt light bulb further away, and we notice that it's maybe a fourth as bright, thanks to that inverse square law of light, we know that the light bulb is twice as far away. You go even further, and we see that the light bulb grows to be about 1/9 as bright as it was, hold it, right up in front of your face. Then that light bulb must now be 3 times as far away. But unlike light bulbs, God did not walk around writing in big Latin numbers and Arabic numbers and Latin script the wattage of astronomical objects. If God had done that, that would have been great. It would have helped us out immeasurably. But he did not do that. So we've got to figure out an object's luminosity via some other method so that we can then use it as a standard candle. So as an example, we know the luminosity of the sun. We could measure that by doing some science here on Earth. And so if we go look out at the sky, take the spectrum of a star and find out that it is the same spectral type as the sun, it's a G25 star, then that means that star should also have a luminosity of 1 solar luminosity, which then, because we can measure its apparent brightness on the sky, we know its luminosity is the same as our sun, we can then get a distance. So that's an example of a standard candle. Now, going out and taking the spectrum of stars all over the place until we find another star that is the exact same spectral type as our sun, it's a lot of hard work and it's not guaranteed to work. So instead, we use a certain type of star, and this is where the Cepheid variables come into play. So Cepheids, for short, these are extremely luminous variable stars that serve as our standard candles for most of the nearby universe. We call them variable stars because they actually pulsate in size. Here's a little animation of what it would look like. They pulsate in size. They grow brighter as they grow larger, and then they dim again as they shrink. And they do this over a period of days or months, days to months. And because of Cepheids, we're not going to get into why it is doing these pulsations. We could have talked about that a few weeks ago. I didn't really want to get into the math and the science behind variable stars and why they do this. Just accept that Cepheids pulsate, physically pulsate. And because those pulsations cause its luminosity and thus also its apparent brightness to brighten and dim in a particular period, we can actually construct a light curve for the star. We can figure out what that period is by watching the star dim and brighten. So for example, a very cool Cepheid variable, RS Puppis, which is imaged here at the bottom left, has a period of about 41.5 days. So every 41.5 days, it will brighten and dim. And we can watch that happen on the sky with our telescopes. Now, this is all fun and cool, but where does this help us actually measure a distance to things? Well, thankfully, in the early 1900s, at the Harvard College Observatory, where Edward Pickering was director, we've talked about this in the past, he had a group of women which he called his computers. Because back in those days, astronomers didn't want to sit down and do all the dirty work of, just like we're asking you to classify galaxies on Galaxy Zoo, astronomers back then still didn't want to do all of the nitty-gritty dirty work. So they hired a bunch of women who were typically able to be paid less than men, even though they still had some of the same qualifications as men. These were very smart women. And Director Pickering tasked one of his computers, Henrietta Swan Leavitt, told her to study the variable stars in the Magellanic Clouds. Those are the 2 satellite galaxies of the Milky Way. And so as she did this over years, she identified just under 2,000 variable stars, of which 47 of them were Cepheids. So Cepheids are rare, but thankfully there's a lot of stars and Cepheids are bright, so we're able to see them. And in 1912, she and Pickering published a paper illustrate with this plot in the bottom right in it. And in that paper, they said that a straight line can be readily drawn among each of the two series of points corresponding to maxima and minima. So in other words, we've got two series of points here. One collection of them is when the Cepheids were at their brightest. The other collection was when the Cepheids were at their dimmest. Okay. The quote goes on, thus showing that there is a simple relation between the brightness of the Cepheid variables and their periods. So let's interpret that. So here we've got the plot. Brightness is on the vertical in magnitude. So bright is at the top, dim is at the bottom. And here we've got their periods. Short period, maybe less than a day. Long period, a few hundred days on the right. And these two plots, so we've got when the Cepheids are at their brightest up top, and the bottom when the Cepheids are at their dimmest. You can see we can draw a straight line. Now this was an amazing discovery because it meant that an easily observable fact about the Cepheids, their periods, which we can just measure by just watching their apparent brightnesses brighten and dim over very human timescales, just weeks, gives us an insight as to their intrinsic luminosity. And because we can measure its apparent brightness on the sky and using this relation, figure out its intrinsic brightness, we can then get a distance to that Cepheid and thus a distance to whatever object that Cepheid is in, whether it's just another star cluster in our Milky Way or maybe the Magellanic Clouds. Now, there's a lot more work that goes into it. There's a lot more work that still is happening that's going into it. But this Leavitt law is very, very important. It's one of the fundamental rungs on our cosmic distance ladder. So for example, here's a little plot I made, some fake data, just give you an idea of what it might look like. If we notice a Cepheid with a period of 30 days, then all we got to do is plug that into the Leavitt law and get that it would have a luminosity of about 10,000 times the luminosity of our sun. Then we can use the inverse square law to determine its distance. It's as simple as that. And so we've used Cepheids to measure distances to galaxies up to 100 million light years away. Thank God Cepheids can be pretty bright that we can see them. So for example, here is once again the Pinwheel Galaxy, Messier 101, galaxy I study. And this little box down here is what this image is showing. And you see all these circled points, C21, C28, C27. These are all Cepheids in the Pinwheel Galaxy, which is about 22 million light years away. And we're able to use the Leavitt law to get us a distance to the Pinwheel Galaxy. All thanks to Henrietta Swan Leavitt. That was a great, great discovery that really, really helped astronomy. Now, sadly, this only works for galaxies up to 100 million light years away. We want to go even further because there are galaxies further out than that. We've got to use even brighter objects. We've got to use even more distant standard candles. And although many different types of objects can be used as standard candles, the most valuable are white dwarf supernovae. So remember that we talked about this 2 weeks ago, I think. Remember that white dwarfs go supernovae once they reach that Chandrasekhar limit of 1.44 solar masses. And because they all go supernova at that mass, presumably, and it is a big presumption of us, they will produce the same amount of light every time. So any variation, any apparent difference in brightness on the sky is solely a function of their distance, of how far away they are, since they all should produce the same amount of light. And thankfully, these things are so bright. They produce maybe 10 billion times the luminosity of the sun. That's a galaxy's worth of luminosity. We can detect them in galaxies at billions of light years away. So here is the spiral, the very dusty spiral, NGC 4526. And right there, back in 1994, a white dwarf supernova happened. And we were able to see it, and we were able to get a distance to that galaxy. So this is one of the best these white dwarf supernovae is one of the best ways to get distances to even further galaxies. The number of galaxies we do this is relatively small, since white dwarf supernovae don't happen all the time, and we've only noticed them for a small handful of galaxies. These galaxies have allowed us to calibrate yet another technique, one that relies on Hubble's discoveries about the expansion of the universe. So now that we know how modern astronomers measure distances to galaxies, let's look at how some earlier distance measurements changed our view of the universe and enabled us to measure its size and its age. So let's back up. So a century ago, a little over a century ago, we didn't know whether other galaxies existed beyond the Milky Way. We called the Milky Way a galaxy, but all the other galaxies, we just called them spiral nebulae. We thought either they could be distant galaxies or just spiral clouds of gas in our own galaxy. So for a while there, the Milky Way was the universe. It was the only thing we knew. And astronomers really disagreed about, are these spiral nebulae distant galaxies, or are they just clouds of gas in our own? And this all came to a head in what we've kind of romanticized as the Great Debate on April 26, 1920. This pitted Harlow Shapley, seen there at the top right. He was a rising young astronomer who the next year would become the director of the Harvard Observatory. So Harlow Shapley against the guy in the bottom, Heber Curtis of the Lick Observatory. Shapley took the view that spiral nebulae were just clouds of gas inside the Milky Way, while Curtis argued in favor of the island universe theory, that all the nebulae, all the spiral nebulae were distinct galaxies. I will say that there was a lot riding on this. Obviously, Curtis at the bottom didn't want to be shown up by a up-and-coming young astronomer. Meanwhile, Shapley, this was sort of a job interview for him to get that harder position. So there's a lot riding on this. And I want to break down their arguments real quick just to see what they were and what people were thinking back then. So Shapley's arguments, remember, he's in favor that the spiral nebulae are just clouds of gas in our own galaxy. His arguments, for one of his points, relied on novae. Not supernovae, but just general novae. We had seen them at this point in the Andromeda Nebula, aka the Andromeda Galaxy. If the Andromeda Nebula were as large as the Milky Way, where we've also seen nova, then its distance would be immense, and the novae in Andromeda would have luminosities greater than that in the Milky Way. He also had used other people's work to back up his second argument that rotation had been observed in the spiral nebula Messier 101, the Pinwheel Galaxy. If that were as big as the Milky Way, then it would be rotating at nearly 5,000 kilometers per second, which is much greater than the Milky Way's observed rotation of 220 kilometers per second. So clearly, these can't be that far away. His big concern was that these things, if the spiral nebulae were true galaxies, they're so far away as to be unimaginable. That was his big kind of argument there. Curtis, remember, he's saying that these are individual galaxies. He said that the novae that have been seen in the Andromeda Nebula, had they been in our own galaxy, they would have luminosities much less than the other novae in our galaxy. And he noted a very recent piece of information that most of the spiral nebulae were moving very fast away from us. How then could they remain a part of the Milky Way? They're going faster than the escape velocity for the Milky Way. So it was, that was his argument. But the debate kind of ended in, we don't know. Neither Shapley nor Curtis had very convincing victories. They didn't have huge convincing arguments. And years had passed before people realized what was wrong with Shapley's arguments. That the novae that he had been seeing in the Andromeda Nebula was actually a supernova, and explaining its surprising brightness. And his rotation argument, a re-examination of the data that the person did of M101 showed that they didn't actually support that plane rotation rate of 5,000 kilometers per second. What really sealed the deal, however, was Edwin Hubble, of course. So after serving in World War I, Edwin Hubble joined the staff at the Mount Wilson Observatory outside Pasadena, California in 1919. And he used its new 100-inch Hooker telescope and pointed it at the Andromeda Nebula and saw individual stars for the first time. This was, oddly enough, still very recent, 98 years ago. Where we've actually only been able to resolve the Andromeda into individual stars for the first time. Additionally, thankfully, some of these stars were our good friends, the Cepheids. And so using, in fact, you can see Hubble's image of Andromeda here at the bottom right, where he's highlighted one star at the top right and labeled it VAR for variable. Using Leavitt's period luminosity relationship, he was able to calculate a distance that was still wrong from modern standards, but it was far enough beyond the outer reaches of the Milky Way that astronomers began to accept the spiral nebulae were actually spiral galaxies of their own. And so our universe got a lot bigger overnight. But Hubble wasn't done there. He and his co-workers then turned their attention to other galaxies and tried to find out how far away they are. Now, other galaxies are going to be much further, so we can't really use Cepheids to a high degree of accuracy here. So instead, they took the spectrum of several galaxies, and they utilized the redshift of a spectrum to deduce the speed at which the galaxy is moving away from us. So remember, the redshift in a spectrum is typically caused by a Doppler effect. The shift to longer, redder wavelengths indicates that the source of the spectrum is moving away from us, and the amount of that shift tells us the speed of that motion. So here's the spectrum of a faint galaxy. So here's what we would, the galaxy originally emits this spectrum of light. But you can see the spectrum that we actually observed, the one on the bottom, is shifted to it by about 5% to longer wavelengths, indicating that the galaxy is moving away from us at 5% the speed of light. So that's how we're able to get a speed out of a spectrum. And using the Cepheids from the nearby galaxies and extrapolating outwards, he was able to make this plot back in 1929, where we got velocity from the redshift on the vertical and the distance to the galaxy from Cepheids on the horizontal. You see, it's kind of a linear line. Yeah, there's some scatter, but it's kind of a line. And so in 1929, he announced this conclusion that the more distant a galaxy, the greater its redshift and the faster it is moving away from us. So this is now enshrined in one very simple equation called Hubble's law. So we express this by V, the velocity of the galaxy, the recessional velocity of the galaxy, is equal to something called h naught times the distance of the galaxy. H naught here is the Hubble's constant, which is a much talked about number. There's a big Hubble discrepancy at the moment. We're not going to get into that. You don't really need to know that for this. But people are really concerned about what value that number takes from measurements. And there's two practical difficulties with using Hubble's law. So Hubble's law gives an exact distance for a galaxy whose speed is determined solely by the expansion of the universe. If that galaxy is in a cluster and gravity in that cluster is causing the galaxy to move at some other direction or towards us, you can't use Hubble's law. There's going to be some extra uncertainties there. Certainly, we can't really use Hubble's law for near galaxies. There's too much extra things happening nearby. We only use it for very far away galaxies that aren't doing much other motion in other directions. And even when galaxies perfectly obey Hubble's law, the distances that we can get from here are only as accurate as our best measurement of Hubble's constant. So up here at the top right is once again another little plot I threw together with some fake data. But you can see the solid line which you can really only make out as we get up to the further distances, is what average Hubble's constant would give us. But uncertainties in Hubble's constant, NH0, gives us anywhere between the two dashed lines. So for stuff relatively nearby, doesn't much matter. If a galaxy is about 400 million light years away from us, then it's going to be moving away at 10,000 kilometers per second. But if a galaxy is moving away from us at 30,000 kilometers per second, then going over here, that could be maybe between 1,200 and 1,400 million light years. So there's a big uncertainty in that distance. So measuring Hubble's constant is very, very important. So let's just briefly revisit our cosmic distance ladder, review all the things we've talked about. So radar imaging happens in the solar system. We measure the Earth-Sun distance by bouncing radio waves off of Venus and using some geometry. Parallax measures the distance to nearby stars in our own Milky Way by observing how their celestial positions seem to change as the Earth orbits the sun. Then, moving on up, we got to use the standard candle of Cepheid variables. Using that period luminosity relationship for nearby Cepheids, we can then use that relation for more distant star clusters and galaxies. So looking at Cepheids in our own galaxy, calibrating that relationship, we're able to then extrapolate it onto, say, the Magellanic Clouds. Then, having calibrated the distance to nearby galaxies with Cepheids, we can then use more distant standards like white dwarf supernovae for more distant galaxies. And then finally, for the most distant galaxies, using white dwarf supernovae distance as the calibrator, we can then measure Hubble's constant, allowing us to use Hubble's law. So that's how we measure distances in the universe. You can see that any rung on this ladder is only as strong as the rungs beneath it. Radar imaging and parallax are on solid ground. Where we start getting into more uncertainties is with the Cepheid variables and the white dwarf supernovae. There's still some uncertainties there. So now, running out of time, I try to limit these only to an hour. Let's briefly end our little introduction to cosmology by using Hubble's law to talk about the age and the size of the universe. So once Hubble discovered that galaxies are moving away from us, moving away from each other, that implies that galaxies used to be much closer together. Of course, we now know that's the Big Bang. But currently the universe is still expanding. It's not contracting, it is going on. And I want to stress that to the best of our knowledge, the universe is not expanding into anything. It is just expanding. As far as we can tell, there's no edge to the distribution of galaxies in the universe. In fact, on very large scales, the distribution of galaxies appears to be relatively smooth, meaning that the overall appearance of the universe around you would look more or less the same no matter where you were located. This idea is enshrined in something called the cosmological principle, that the universe has no center or edge, and on large scales looks about the same everywhere. And we can't really prove this principle to be true. It's still consistent with all of our observations. So now I hear you asking, how can the universe be expanding if it's not expanding into anything? Well, let's use a balloon as our analogy. So we're only going to be talking about the surface of the balloon. We're not ignore the air inside the balloon. Just talking about the surface to represent the two-dimensional surface of the balloon to represent all three dimensions of space. The surface of the balloon represents the entire universe, and the spaces inside and outside the balloon have no meaning in this analogy. So let's use this balloon analogy to see how Hubble's law leads us to an age estimate of the universe. So for example, imagine that some miniature ants, some ant scientists, are living on dot B in this image. Suppose that 3 seconds after the balloon begins to expand, they measure the following. Dot A is 3 centimeters away and is moving at 1 centimeter per second. Dot C is also 3 centimeters away and is also moving at 1 centimeter per second. And dot D is 6 centimeters away and moving at 2 centimeters per second. So these observations are exactly what Hubble's law would tell them to expect. More distant dots are moving away faster. Moreover, because these miniature ant scientists have measured distances and speeds for multiple dots, they have the information necessary to discover their own version of Hubble's law. So recall that this law can be written as V is equal to Hubble's constant times the distance d. So for the balloon, the velocity v and the distance d would represent any dot speed and distance. And the Hubble's law for the balloon would be something like v is equal to 1/3 seconds times the distance. Now, if the miniature scientists think about their balloon as a bubble, they might call the number relating distance to the velocity, that 1/3 seconds, the bubble constant. So an especially insightful miniature scientist might flip over the bubble constant and find that it is exactly equal to the time elapsed since the balloon started expanding. That is, the bubble constant of 1/3 seconds tells them that the balloon has been expanding for 3 seconds. So maybe you see where we're going with this. If we invert our universe's Hubble constant, not the balloon, but our own universe, it could tell us something about how long our universe has been expanding. So 1 over the Hubble constant gives us about 14 billion years, which is more or less right with other ways to measure the age of the universe, about 13.8 billion years. Now, an expanding universe actually does introduce some complications, as everything tends to do in astronomy. When we want to talk about large distances, if a galaxy is really far away from us, then it's moving really fast away from us. And so it is moved even further by the time its light has reached us. So astronomers get around this problem by talking about a galaxy's look-back time. We find it more useful to describe the galaxy's distance by using the fact that its light has taken 1 billion years to reach us. That is the look-back time. For example, when astronomers say that a galaxy is 1 billion light years away, we usually mean that the galaxy has a look-back time of 1 billion years. We have a similar problem with redshift. Is this redshift caused by a Doppler shift of the galaxy physically moving away from us, or is it caused by the expansion of space? That space is expanded, causing the galaxy to appear to move away from us, but in fact, the galaxy is staying still, and instead the space between us and the other galaxy is expanded. So this other one is not a Doppler redshift, but a cosmological redshift. And for distant galaxies, astronomers actually find it useful to think of it not as the galaxy physically moving away from us with its own precessional velocity, but actually the space between us and that distant galaxy is expanding. Thus, we call it a cosmological redshift. So galaxy's redshift, therefore, tells us how much space has expanded during the time it took for the galaxy's light to travel to us. And its look-back time tells us the distance its light has traveled. And then finally, the last kind of mind-blowing thing is when we began our discussion of the universe, I stressed the universe has no edge. But there is, the age of the universe does actually limit how far back we can look in time, how far away we can look. And so there is no edge to the capital U universe, but there is an edge to the observable lowercase u universe. We call that the cosmological horizon. And so the cosmological horizon is the distance at which the look-back time equals the 14 billion year age of the universe. And calculations from general relativity tell us that the horizon is about 47 billion light years away, which you might notice is strikingly larger than the 14 billion year age. That's because space has been expanding at a non-linear rate. It's been accelerating. So it's grown, we're able to see a bit further back than the age would tell us. So before we get into all those big complications, and we will get into some of those complications in a more detailed method in a few weeks, we'll stop it here before I blow your minds even more. And as I stress every week nowadays, we are doing astronomy. You can go outside and look for the things we're talking about. So we've talked a lot about different galaxies tonight. So over the coming nights, if you've got a telescope, at this point you will need a small telescope to see these things. Well, actually, strike that. I'll correct myself. You'll need a small telescope to see this first object. You don't necessarily need a small telescope to see the next two. So if you go out tonight, this is Cleveland at about 11 p.m. Over the coming night. You don't have to go out tonight. Look towards the northwest, and you should be able to find the Big Dipper. Near the Big Dipper is the Pinwheel Galaxy, the galaxy I study, Messier 101. You can go see that. If you can't see it, there's an image of what it should look like from Hubble. Nice, beautiful spiral galaxy. You don't necessarily need a telescope to see the Andromeda Galaxy. It's bright enough that if you're in a dark enough spot, you can probably see a fuzzy patch of light on the sky in the northeast to east, near Cassiopeia. Let Cassiopeia guide you towards that fuzzy patch. You should be able to see the Andromeda Galaxy with your naked eye in a dark enough spot. If you can't, if you're like in the middle of the city, then this is what the Andromeda Nebula, the Andromeda Galaxy looks like. And then the last one, you've got to be in a really dark spot to see this one, but just below where the Andromeda Nebula is, sorry, I keep saying nebula, the Andromeda Galaxy is, you should be able to see the Triangulum Galaxy. The Triangulum Galaxy is one of the furthest objects that you can see with your naked eye. If you can't see it because you can't get to a nice dark spot, you've seen it in the background of all these slides, but here's another image of it. So that is the end for now. Next week, we'll talk about galaxy evolution before jumping back into some more cosmological discussions. But it looks like we have got 4 more talks before this is all over. So 4 more weeks. So as always, leave a comment down below, like, comment, subscribe. If you have any questions, I'd be happy to answer those. But otherwise, I will see you all next week. Have a good night.